Yes, I can hear you.
Is that a yes or no? Sorry. Can you hear me properly?
Yes.
Give me a thumbs up if you can.
Yes.
Perfect. Okay, awesome. All right.
So we'll start recording and then
Yeah.
you're ready to go. All right.
Good to go?
Good to go.
Awesome. So I am Aafaque and the talk title is aligned with, it's hiding my talk title. A spirited ultraviolet mission to map the ghostly gas around galaxies, just to match with the ethos of the day. I love that people are here in costume. I took off mine, but my costume is a grad student looking for a postdoc. That's pretty scary. You all have been there, at least some of you. So before we go into the actual talk, I wanted to talk about my before life, what I did in my life before I started doing Aspera. And that is, I was the lead engineer, because I saw a lot of solar people here, and I'm at LASP. I was the lead engineer of the Solar Ultraviolet Imaging Telescope. It's UV imager. It's the size of, that's a meter long optical bench, about 70 kilogram payload. I led the end-to-end design from baseline design all the way to CDR. The instrument worked. That's the testament of my success. It was launched in 2023 and still giving full disk images of the sun in the near ultraviolet bands all the way from 200 to 400. There are 11 different filters. And we are covering the photosphere, chromosphere, and the transition region, full band, and also doing region of interest images of active regions and flares and stuff. And the data is public, so you can look at it. But that was a fun ride, and then I decided I want to do a PhD. I don't want to be an engineer, and so I quit and I went to College of Optical Sciences at University of Arizona as a master's student. Soon realized that I don't want to be a master's student in optics, I want to do a PhD. That was the original goal, so I transferred to the astrophysics program at Stewart Observatory, University of Arizona, where I work with Erica Hamden and Carlos Fergus. And our group's focus is to see this gas that allegedly nobody has seen before. And I'll talk a little bit more about that. And this mission, Aspera, is all about doing some pioneering science from really small platform. Again, something that Colorado is also a great place to do. So let me give you some introduction, scientific background. This is the hydrodynamic simulation of a single galaxy zoomed in, and it's showing how the gas density, gas temperature, and star formation evolves over time. You see all this gas that's flowing out of the galaxy. We have never mapped this gas. We haven't seen it. We have seen it through some proxies, but it's very difficult to measure because the densities are really low, the temperature scales are really high, and also the morphology is unknown. So we don't know how much per fraction of what temperature gas is present. We know that there are metals. We know that they are in low density from absorption-line spectroscopy with background quasars, but we don't know how much of this gas is. So there's uncertainty on what quantity of this gas exists, but there's no uncertainty on the fact that 30% of the baryonic mass of a galaxy is missing. We can't account for it. And current belief is that most of that mass is in this circumgalactic and intergalactic medium. And mapping this medium is vital to understand how galaxies form and evolve over cosmic time. So here's what we see, what we know. This is actually one of the Aspera targets, and you see 4631. Trying to get rid of this, but
I think if you said okay.
I'm sorry. Yeah, so I love this quote by Proust, who says, "The real voyage of discovery consists not in seeing new landscape, but in having new eyes. And through our ultraviolet eyes, we are trying to map this gas. So currently, the state of the art is that you look at a galaxy, you take an image, you see something like this, and then you say that's the galaxy. What I say is, no, that's not the galaxy. This whole distribution of gas, where some gas is flowing in from the circumgalactic medium, there is gas that is being expelled by the AGN at the center of the galaxy, the gas that is being expelled by supernova explosions. all of that is a part of this cosmic ecosystem in which galaxies evolve, and galaxy evolution cannot be understood completely if we are not able to make images like that. And so the whole quest is sort of to be able to map galaxies, circumgalactic medium in emission. And why is it hard? Because at least for the nearby galaxies, all this emission is happening in X-rays or near ultraviolet, and near ultraviolet instrumentation is pretty challenging. The optics coatings are, they don't last very long if they are exposed to room air. They are hard to make. There have been pioneering work that has made it easier to make high-quality optical coatings that can give you 60 to 70% transmission. And I know some of you who work in visible or optical might be like 60%. That's bad. But 60% in UV is like we'll be celebrating. And then the detectors are also challenging. Traditionally, photocathode laden microchannel plates detectors have been used, and for instance, for HST, 10 to 20% quantum efficiency on those detectors was state of the art. Things have changed drastically, so we have better quantum efficiency detectors, both channel plates and solid state, and we have better optical coatings, and we now have these smaller platforms on which you don't have to wait to build like the next $200 million telescope to be able to do the science. You can do some of it from these small platforms. So Aspera is the size of a mini fridge. This is the spacecraft, and that's the instrument. The instrument has two spectrographs in here. They have a long slit, and in ultraviolet we typically try to minimize the number of bounces, so it has just two mirrors or two optical elements. One is a off-axis parabola that focuses on a slit, and then there's a grating that disperses light onto a detector. And then because it's a small mission, cheap mission, the two channels or the two spectrographs share one detector, because the detector is the really expensive part, about $1 million. And what Aspera will do is, I want to emphasize this, for the first time, measure the ultraviolet emission. And what we're trying to do is trace this warm hot gas with oxygen 6, because one, it's the highest density ion at that temperature, about 10 to power 5 to 10 power 6 Kelvin, and it's the one that we can track in the ultraviolet. So the emission from oxygen 6 is at about 103.2 nanometers, and by putting long slit and kind of scanning it across the galaxy, you can then create an image. So this is what simulations predict, the distribution of this warm hot gas as traced by oxygen 6, and that's what Aspera is capable of if we are able to slew across the entire galaxy. Obviously, the observing would look slightly different. I'll talk a little bit about it. But detect this emission from 10 galaxies, the single slit, so just one slit, and be able to detect above and below the galaxy's disk if there is oxygen 6 emission. And that would put on constraint on what the quantity, how much oxygen 6 is there, how much of that gas is emitting. And then map 3 of these galaxy targets to create a map like that. And this has never been done before. So this is how the actual observation would look like. The detection observation would have just one slit, but with this you can still do scale height versus the density of the gas, and then the mapping campaign would do up to a 50% fill factor observation by putting these slits at multiple locations, and again scale height versus the position, and then that can also tell us kinematics, because as per the spectrographs, we would be able to resolve different velocity components of oxygen 6 up to 200 kilometers per second with centroid sensitivity of 30 kilometers per second. What enables Aspera, as I've talked a little bit about, is state-of-the-art coating that were developed at Colorado in collaboration with NASA Goddard and JPL. Channel plate detectors that are not your mom and pop channel plate detector, not the HST channel plate detectors, but state-of-the-art, so they get 50% quantum efficiency in the ultraviolet, almost zero channel plate detectors, so no background photon counting. Slits that are commercial off the shelf, so really cheap, but still be able to meet precision requirement. Baffles that we are able to use optical coatings that are really, really black, so that you can suppress the stray light in the instrument. And then be able to point really well because you want to be able to repeatedly put your slits. So we have a star tracker that's attached to the instrument but commands the spacecraft to be able to body point the spacecraft. And then electronics that we have developed at University of Arizona in-house. So the focus of my talk today is to give you an overview of the journey of what it takes to build an instrument like this. This is a university-led instrument, so it's not being built at a NASA center or at a defense prime contractor. It's being built at a university, and so it has a flavor of being able to do that with grad students, postdocs, and early career folks. So I am the alignment lead. I'm a graduate student, alignment lead of Aspera. What we had to do was we had to bring in these really precise, these optics to a very precise alignment. And although I said that Aspera's optical coating are not that sensitive to contamination anymore, they're still sensitive to contamination. For instance, if you leave them out in a room at 70 relative humidity, 70%, and wait for a week, their optics will be dead, or they'll not be useful for your mission anymore. So the alignment has to happen in a controlled environment inside a nitrogen purge, and the precision that we needed, because we are inside a really tiny box, we needed like a 5-micron precision to be able to align the optics together. So these are like challenging things to achieve. So the way we did this was we used optical interferometry, and by that what I mean is we have collimated beam of light comes in from a interferometer, which can measure the wavefront. It hits the mirror and then bounces off this computer-generated hologram. The computer-generated hologram is programmed in such a way that if light comes at certain angles at it, it'll just return the light back. And for the off-axis parabola, half of it is being used to align this OAP. So the light hits the hologram, goes back into the interferometer, and that generates the wavefront pattern or the interference fringes. From those interference fringes, you can interpret how far out is this optic from its the desired position. And we do the same with the grating. So the grating, although our ultraviolet gratings, we are using a laser light which is at 632 nanometers to do this alignment. And the way we do it is use the 0th order of the grating. So the green light, so if you ignore this, let me actually go to the next plot, so makes it simple. The green light is the bottom half of the green light is the bottom half of the mirror. The light from that goes all the way to the grating through this computer-generated hologram substrate, which is just UV fused silica, and then bounces off the grating, hits this pattern, and is returned back. So then you can move the grating, see the interference fringes, and based on that, basically do null interferometry and null your grating into position. And so the hard part was that how do you do this on a really small instrument where everything is so crammed up? So we built these mechanisms that hold the mirror in position, moves it around, and locks it in one position. Then you can tighten some screws for the flight hardware and remove the red part. So that red part is the GSE. And all of it is controlled fly-by-wire. So we install this, we put a cover on, we have an opening so that the laser light can go in and out, but the whole instrument is under nitrogen purge. And then we control the mechanisms, all of them, by software, looking at the feedback from the interferometer. So this is just the setup. The interferometer is placed over here. The light hits this fold mirror and then goes into one of the channels of Aspera. And that was, again, a thing that we had to invent out of necessity because we didn't have enough big enough beam to align both channels simultaneously. We placed a fold mirror that would help us align one channel, lock one channel. Then this mirror can move on this stage. We have some references that allow us to keep the alignment of this mirror with the interferometer. We go to the next channel, we align the second channel by moving these mechanisms. And this is what you get. This is like a fringe pattern from one of the optic, and what you see here is like a astigmatic residue from the optical surface. And if it's not aligned, you either don't see anything or you see lots and lots of interference lines. When you have positioned the optic at the right position, you start seeing very low wavefront error. So that's the idea. And we kept basically moving the optic till we got that. So this is the wavefront measured from the final alignment. This is the results we have removed the tilt because the tilt is degenerate in these kind of measurements. So we get about 0.3 lambda and 0.158 lambda RMS wavefront errors, and those correspond to about like 5 micron precision in the positioning of the optic and about 5 to 10, 15 arc minute of tilt, which is within our requirement. But and this is the other channel. There were challenges because once you try to position and align and lock these optics down, even just the process of locking things down can shift things around. So the expected part was that it's going to be hard, and the outcome was it was extremely hard. So it took us a couple of attempts. With the alignment scheme that we had developed, the advantage was with the fly-by-wire and the interferometric feedback, we were able to repeat the whole alignment in a couple of days. It would take traditionally a little bit longer, a few weeks probably, to do such an alignment, but we were able to shrink this into a few days because we were also trying to save time for the instrument to be exposed. So then the next set of steps was, this is just the steps that we go through to position the individual optics. So there is a lot of stuff that is going on beyond what I explained. I don't want to go into the detail. I'm trying to read the room, and so the process of aligning the slit is also challenging because there are 2 instruments, and we want both the slits to point at the same part of the sky, at least to within 30 arc seconds. Otherwise, you get a googly-eyed payload, and you can't co-add them to basically increase your reduce your noise. So for that, we basically had to place a slit at the focus of the OAP while not disturbing the rest of the optics. So this is the slit, and then have the beam from that interferometer go into a microscope camera. And because the focus of the OAP, we have done the alignment with the OAP with the interferometer, there is a fixed focus for the on-axis beam. And that's where we want to place our slit. The slit center should be at the best focus location of the OAP. We create an image of the slit focus in this camera and bring in the slit and look at the slit itself till it comes in focus. And that means your slit is now looking at the same place as the focus of the OAP, and that's how we align the slit. And this is how this, so again, the cartoon looks easy. The setup was quite challenging because you had to build something that bridges over the payload. These are our slit mechanisms, and the adjustment level that was needed was like for defocus, we are talking 50 micron precision. For decenter, it was about 30 micron precision to position the slit at the right location while you're working with an optic that is contamination sensitive, so there's a limited amount of time you can open the cover and make the adjustments. For the slit, we had to do these adjustments mechanically by hand. And then we had this camera setup, which is actually a microscope, so it's like you have to magnify everything to 50x. So this is the beam splitter that you saw in the cartoon, and this is the whole camera setup. Much more complex than the cartoon layout itself. But it worked. This is a true focus image of the PSF of one of the channels. So somewhere over here is the best focus, is where we say 0 for the alignment reference, and then we bring the slit in and shift it slowly to try and get it best focus where the PSF is already at best focus. And you can see the image is really sharp. The problem was that this laser is so bright that you can't get both of them, the slit image and the laser image at the same time. So we had to turn the laser off, but the blue crosshair kind of represents where the laser is. So we are centered within 15 arc seconds on the slit, and we are and from this images you can actually back calculate the defocus, so we're within an uncertainty of 10 microns within our tolerances. Again, this is the hardest part. So all of this is optical, so it's still easy. Like there's nitrogen purge, so you can do this, but then you have to put the detector in. And the funny thing about this detector is it has a photocathode which has cesium iodide on it. Cesium iodide reacts with air, mostly water in the air, and dies within 20 minutes of exposure, 20-25 minutes of exposure. So the detector actually stays in vacuum and a door stays shut. And unfortunately, at Aspera's wavelength, the material that is the window of the detector does not transmit 103.2 very well. So you can't just have this window shut and do the alignment, you basically have to open this window and somehow be able to focus light. And then all of this was laser light. The grating would not direct the beam from the laser at the focus. So you have to actually use 103.2 nanometer wavelength. And to generate that, we have to have this very crazy setup. There's a high voltage flow lamp that operates at 1.5 kilovolt. We flow hydrogen and argon through it, and that ignites the hydrogen argon. So we're generating light from this plasma. We have a monochromator that takes out the excitation at 102.6 nanometer and 104.8 nanometer, and then puts it into this telescope. And luckily we had this telescope from another rocket program. We just replaced the coatings of this telescope, and at the focus of this telescope is the focus of that monochromator, and then this is like operating a telescope in reverse, so we get a collimated beam out. We put our payload in there, and then the payload itself is spectrograph, so it can disperse the two wavelengths that come out of the thing, and then you can use those two wavelengths, the green and the blue, move the detector while it is in vacuum to focus the detector. So that's the challenge. And we are not using the red, which is the wavelength at which Aspera is optimized, because not a lot of gases emit at that wavelength, specifically the one that you can generate in laboratory. You need a much more sophisticated plasma source to generate oxygen, and when you try to ignite oxygen at high temperatures with hydrogen in it, that is an explosive process. So we don't get a lot of oxygen 6 or any emission that's around our wavelength. We use these two lines that are in proximity with our wavelength to kind of focus it. This is how the setup looks like. So we bring the payload in to this tank, and one of the challenges is to be able to align the payload itself with the rest of the rocket. So we use interferometry to align the rocket first, and then align the payload's bore site with the rocket optic bore site in order to get the collimated beam into the instrument. Again, because the slits are only 30 arcsecond wide, the payload cannot do more than that in terms of its own tip tilt when we are trying to do this alignment. But we did position the payload in the tank. There is a more elaborate figure that kind of shows different elements. That's the monochromator over there. That's our argon gas supply line. This is a very big vacuum chamber in which everything sits. That's me trying to close that door, although it's an one-person job. You can lose a finger trying to do that. And then this is how the payload looks like when it was in there. That's the detector. And the last part of the trick is, again, the detector has this mechanism on it by which we can operate it fly-by-wire inside the vacuum. So we don't have to bring everything out of the vacuum and adjust things and then close it and pump everything down, because that's almost like a couple of days of vacuum cycling. So if you want to make one adjustment, you would take 2 days to make that adjustment. That's really painful. And so this is very not sophisticated but involved mechanism. 3 different motors that can push things at the accuracy of plus minus 20 microns. And then we basically are able, for the detector, we only needed to tip tilt it and defocus it within a plus minus 200 micron range. Again, a fly-by-wire software was written by me to kind of do this. And sort of what we look for then is take an image with the detector and look for this spot and see if this PSF becomes minimized. So use 80% encircle energy of this PSF. And so we have 2 spectrograph channels, and we have 4 lines. The argon line, the hydrogen line for each. So there are 4 lines, and we want to make all of those spots of a certain size. So we have to go through focus. This is like an image of moving through focus and trying to minimize it. That's from the argon lines on the top for the 2 channels, and this is from the line beta line from the 2 channels. And the trick was that this is not best focus. You are actually away from the best focus of both lines. This one's best focus is here, that one's best focus somewhere over there, whereas your oxygen 6 line's best focus is here. So we had to go through focus, figure out where the best focus of the 2 lines are, and sort of average location is where the oxygen 6 best focus would be expected. And that we'll not know until we go into orbit. So that's the tricky part of this kind of setup. But we were able to do this alignment. and we all go for calibration. However, space is hard. So 10 months, this is a summary of 10 months of just work in the lab and probably years and years of preparing, designing all of these setups that we talked about. And so we went in, we were running our detectors, we were able to get light onto the detector, but after being in vacuum for about a month, we started to notice some current spikes in our detector. And eventually we were not able to power our detector. Aspera's detector operates at about 3 kilovolts. So there is a specialized power supply that supplies this detector. These detectors are extremely robust. They have flown to Juno, they have flown to Pluto, they have been in very robust radiation environments. So they themselves are pretty robust, but they need these specific power supplies to be able to supply that 3 kilovolt, and because we're doing photon counting, to be able to not have any background noise, we need the power supplies to be extremely stable. Designing these power supplies is not trivial. We made an attempt. We got a lot of help from our friends here at Colorado. We built it, we put it in, we were running it, it worked, but after 3 weeks or 4 weeks of operation, it failed. So we were able to do some of the activity that I talked about, and the reason why it failed was that one component was a failure mode. And so this is like a $20 million mission, now on hold because there is a failure mode. And that's me on the day when somebody took this picture and we pulled the payload out for diagnostic, and I was trying to see if we can recover from this, and we realized no, it's not going to happen. And so we had to, for recovery, we had to pull the power box out, put it back in, and hopefully pray to God that the alignment has not been screwed. All the work that we did for 6 months has not been screwed, because we're not expecting to take this electronics out of the crate once it was done. But we did a R&R and replaced it with a flight spare unit. That worked, and so most of the results that I showed you, the data was taken with the flight spare unit. We locked the detector in position at best focus, but unfortunately the flight spare unit has also failed. So now, and again, the same reason, this is what happens. This is inside the epoxy, one of the connectors. The diagnostic, we can go in if you are interested, you can go offline and talk about it. But basically, there are small air bubbles around this connector. When we pump everything down, they still stay at atmosphere, but leak slowly. And this high voltage, it's hard to break it down in air, but as you reduce the pressure, the breakdown happens really quickly, and that region is called the Paston region. So once these bubbles go into the Paston region, they just create a shortcut path, and so we had a short circuit in our power supply. So this box in question and this connector in question, and then there are some power supply modules over here that are also in question. So we're trying to now work with Southwest Research Institute and also rebuild a version of our hardware, and we're still hoping, because we are aligned, replacement power supply would come in and we would be able to verify our alignment, do calibration, and be ready for launch. Aspera spacecraft, this is being done at Space Flight Laboratories in Toronto. That's the payload. It's in almost ready state. The baffles and all will go in after we have replaced the power supply. We'll do a calibration of the instrument to verify its alignment. Then it goes into shake and bake, vibration and thermal vac testing, after which it will go and get integrated into the spacecraft. And we are still expecting to launch in late 2026. We'll be on we have a launch manifest with Rocket Labs. Currently, we're scheduled in late August. We have a countdown set in our department, so there's no pressure at all. It's in the lobby of the department. You walk in and you see that countdown, and you're like, anyway. So there is a wall clock which we are up against, and that doesn't say 300 anymore. It says 259 days to go. Anyway, so that's the instrument part. Do I have more time? Yeah. Couple of minutes. Okay. So I'll just quickly punch through the science, because that's what you might wonder. Oh, instrumentalist. I am like a complete instrument nuts and bolts guy. But the reason why we do this hard things is because we want to do some great science. So I introduced you to the science that Aspera will do, but there is science that Aspera can do, and that's part of the thesis work I did. Was Aspera is traditionally designed to, like, the design is to do this 20-minute radius around a edge-on galaxy, measure some gas above and below the disk for the first time. But then I found that there's actually an interaction happening between the LMC and the Milky Way that can be traced in oxygen 6. So recently some group have reported that through quasar absorption line studies of from COS, they found that there is some warm hot gas emitting in oxygen 6, carbon 4, silicon 4, around the interaction region between the Milky Way and the LMC. And it's claimed, because the line of sight velocity, it's claimed that this gas is actually associated with LMC, which is a dwarf galaxy. So it's like a corona or a CGM around a dwarf galaxy that's also in a merger. So we are trying to ask this question: what happens to the CGM in merger? And Aspera can solve this, give some clues to this problem. If we take the slit, which is designed for this 1 arcminute by 1 arcminute spatial bin, but then bin all across it, six of these over this 1 degree slit, you would be able to reach about 1 line unit plus. If we are able to put these slits around that region, you'd be able to do at least like a radial profile of oxygen 6 around LMC going towards Milky Way, the direction in which LMC is moving, and the spectral resolution of Aspera is sufficient to be able to resolve whether the emission is coming from Milky Way or LMC. And then we can distinguish scenarios like this where there is a Bow-Shock. This simulation was done by Chris Carr at Columbia, who's showing an idealized hydrosimulation of what the gas density would look like. And specifically, he's also now working on predictions of oxygen 6 emission. But what that part, the purple part, is mostly the diffuse Milky Way CGM. This is an interaction region where there could be a potential Bow-Shock. Behind that Bow-Shock, the state of the gases was also sampled, and they found that it also contains this CGM emission of warm hot gas. And then the trailing gas also is connected to SMC and the large Magellanic Trail that I was trying to show. So there's a question: is this trail partly formed by LMC losing its corona and that gas then getting entrained and being cooled and forming this cold gas behind? What is the origin of this Magellanic stream? What happens in this interaction is a question that can be answered with this additional Aspera study. And we would actually do better than what Aspera does in depth because we are bidding. So you'd get to 1,000 line units in just 6 hours, and you could put 25 of these in a month, and about 100 of this in 4 months. And the COS halo, the entire study of COS halo absorption line studies that were done for this region was 100 quasars. So the limit of line of sight absorption studies is that you can only trace the gas through the quasars, but with emission mapping, you can place the slit wherever you want in the area of interest and be able to do much better than what Hubble Space Telescope did in just 4 months. And so the survey would look something like this, trying to trace this gas. We don't know where it is, so we would also find out what the extent of this interaction is. And so Aspera would be able to do that as an extended mission that I'll lead. Thank you so much. Questions? Yes?
I have a question. So this is a really cool talk, and I don't really do too much instrumentation stuff. So it's such a bummer that the power supply failed. When that fails, did that affect anything else, or is there like safety precautions that
That's a good.
That short circuit didn't affect?
Good question. The software, the flight software was built to handle these kind of things. So we saw a current spike, but immediately, as soon as you see the current spike, the software just shuts down.
I see.
So we have inbuilt precautions, so nothing else get affected. We have checked out the detector, and the flight detector is fine. Everything else that is associated with this. Luckily, the high voltage supply is also its own isolated line, so if the high voltage is failing, it doesn't affect anything else on the system because it's powered separately.
I see.
Yeah.
Very cool.
Yes?
When your HPPS fail happened, was that with your flight spare detector or with your flight detector?
It is with flight detector.
Okay, so you've already done all of the alignment, redone all of your alignment with the flight detector.
Yeah, all of the stuff we have done here is all flight detector. The spare we haven't touched. We have not invoked the flight spare detector yet. The flight spare detector is just sitting safely. Only the power supply is a problem. The flight detector is still completely fine. We checked it with a separate power supply, commercial one, to make sure that it's working properly. So background and all the diagnostics of the detector come out proper. Yes.
Excellent talk.
Thank you.
So you mentioned that you were concerned about degradation on your optical coatings.
Yeah.
Are you all actually seeing degradation on elusive?
Good question. We haven't really had bandwidth to track it, but we are tracking it with the coupons which we'll measure. We are currently controlling the exposure in such a way that at this point we will not even be able to measure that degradation, to be honest. We have never exposed the optic above 40% humidity for more than like 10 minutes.
Yeah.
So we don't know. The answer is we don't know. Once we do the calibration activity, we would be able to back out the effective area, and from there the throughput.
Yeah.
And that's when we'll be able to tell. We have some coupons sitting in the lab, but honestly we haven't had the bandwidth to track them. Those coupons are traveling with our optics, and we have some controls that are sitting in the clean room. We'll do some calibration measurements once we get to that.
I'd be really interested to see if you actually see any degradation on elusive, because we haven't.
I think that's what we are hoping. A lot of the stuff that we are doing is just based on the work that you guys did, and be like, okay, you have shown that at so and so humidity it's gonna die in so and so time. Let's not expose it to that. And then the lower humidity exposures, every single exposure, every time we take the cover off, is logged, and we keep an eye on our humidity exposures to make sure that we are never exceeding what's required. So far we've done really well. We have probably exposed cumulatively less than 7 or 8 days of humidity exposure in regular clean room humidity. Yeah.
I don't want to. Okay. So for both of the alignment environments that you showed, both the one with the one at air, and the one in the tank,
Yep.
the detector. Both of those are relying to some extent on something else being focused. So, for example, with your where's the one with the rocket mirror? Yeah, or that, sure.
Yeah.
So for
Sure.
that one, when you're aligning the slit, you have like the microscope camera. How do you check the focus of the microscope camera? And with that, like similarly, how did you check the collimation of the beam that you made in the tank?
So because this is like an example of confocal microscopy, so it is self-calibrating in some sense. We don't have to worry about if the microscope camera itself, so there is some aberration associated with the microscope itself, but these microscopes are designed for looking at really, really tiny things, so the aberrations from the lens of the microscope are really small, and we verified that.
I'm not talking
Right.
about the
Yeah.
aberrations, I'm talking about the actual focus. So like, if you have a perfectly collimated beam going into the microscope
Yep.
camera, what spot size would the microscope camera create?
Yeah, so that we know, and we have tested that. And we get reports for the microscope camera performance. We model that in ZMAX as well. And then the collimated beam doesn't go into the microscope, it's the diverging beam after the focus.
Right.
Yeah.
And
so we are re-imaging, because we already know from the CGH alignment, right? We already know that the OAP focus is where it is supposed to be. Because if it's not well aligned with CGH, then we would not get the feedback we get. And CGH is actually sensitive to much higher tolerances than we can align it. We see that wavefront error there. And so we know that the OAP is at its best focus. When we measure the PSF in our camera, we see a small enough PSF to say that there is some aberration from the microscope, but this PSF can only be achieved if the microscope plus the OAP are very well aligned.
Cool.
That's the self-calibration.
in the tank with the parabola that you're using to create the collimated beam,
Yeah.
I guess how do you measure the collimation of that?
Good question. So for the that's a full telescope, and the primary mirror is actually a sphere, but the secondary mirror is a sphere, and that corrects for all the aberration actually. Let me see if I can get back to that. So this guy is in a sphere, and the telescope is really slow. The F number is 30. So we put a laser source at the focal plane of the telescope and then check the collimation with the laser. But also, to just align this telescope was not aligned. This whole setup was built for Aspera. It was sitting in somebody's garage, in a lab. And so we had to get these optics out, recoat them, and set them up. And for that alignment, we used the interferometer. What we did was we had the collimated beam from the interferometer go through the system. At the focal plane, we put a sphere. And so that sphere gives a retro, so we interferometrically first align the telescope. That also guarantees a collimated beam back if you put the source at the sphere location. Then we remove the sphere, and then mechanically where the sphere was is where the slit of the monochromator is. So that's how we get a collimated beam out, and we actually put a laser light through the monochromator and the collimator and the whole telescope to check the collimation again with the laser. And once we had the monochromator installed, we used a green laser with a variable aperture, so we could simulate as if light is coming from the slit focus, and so we still could check collimation. Any other questions?
Oh, gosh.
Yes.
Quick one.
Please.
Light units. What is that unit?
Oh, I'm sorry.
Explain that, like in terms of maybe.
Let me try and pull that out.
Other units.
Let me try and pull that out.
I saw 5 times 10 to the negative 19.
Yeah.
For per second, and I'm wondering what that corresponds to.
That's 1,000 line units.
Okay.
About.
Okay.
Sorry, I should have the line unit is an abstraction I use in papers, but I define it somewhere, but in this talk I forgot to do that. So 10 power minus 15 ergs is about 1,000 line units, and that's what Aspera is trying to get to.
Mm-hmm.
The mapping will be about 10,000 line units, because the mapping, because we're trying to raster it, it's slightly lower exposure time. But these are still numbers for emission. So there are only like 4 detections of oxygen-6 from fuse, and those are at those levels. So we determined that our lowest sensitivity is based on past detection that were made with fuse, but there are only 4 of them, and they're like serendipitous detection. There's no spatial resolution around them. They're almost like point source detections.
And I'll ask another one.
Yeah.
What is that simulation?
It's foggy.
It is foggy.
Foggy, Lauren Corliss,
yeah.
and David
Is
Schindler.
she at
She was, no, she's not at Arizona. She's a part of the Aspera team, because David is part of the Aspera team, and then she did the simulation for us for our, and I thought she moved out, and now I think she's at Harvard, if I believe I'm right.
Yeah.
She was in transition, she was figuring out.
She went to LSST, so she was
yeah.
for a different reason. But
She went to LSST for a different reason, I think, yeah. Anyway,
nice talk.
thank you so much.
Okay, 2 quick questions. You mentioned a couple of space resolution numbers in this talk. So one being 120 arc seconds,
Yeah,
one being 30 arc seconds, one being 78 arc seconds.
sure.
Can you explain a little bit?
I definitely, good question. 120 arc second is the requirement from the top level science drivers. Our slit width is about, initially when we designed it was about 30 arc second. Now we know that's actually 36 arc second, the slit width on sky. And then when you try to add 2 slits, we are not getting a perfect alignment. So when we do that co-addition, we are creating an image from 2 different slit pointings, and the effective resolution would be around that 70. So these are numbers different because of the margins that are built into the design. I hope that answers the question.
Yeah. And just a quick question. When you were focusing in vacuum, what lines were you actually focusing with? You mentioned some argon lines. What's the wavelength?
1026 and 1048. So
you open the window.
We have a mechanism to actually deploy the window like we do in space.
Right.
And then we have those lines hitting our detector.
So you didn't do any measurements with the door closed, with the window closed?
We can't, because the way, it's a design choice that was made for Aspera, which I don't like, but the way the spectrograph was designed to share the two channels, we don't get higher wavelengths. We don't get Lyman alpha, for instance. Our cutoff for the optical performance becomes really bad, and then our sensitive, the light goes out of our sensitive area. So our sensitive area is about 5 nanometers wide at max. 101.1 to 1040, 1068, because in one of the channels we actually see some part of the 1068 argon line, in the other one we don't because of slight decenter. But yeah, that's a big challenge. That's one design choice I would not make if I'm designing another mission like this.
That makes it hard for sure.
It makes it really hard.
What's your process for closing the window again?
Good question, by hand.
Just open up chamber real quick and just go.
So what we did was, this chamber has a gate valve on it at the back, very big to attach the rocket. That's why I call it the rocket tank. And so what we do is we first purge the setup completely. We open the rocket tank, put a humidity sensor right there, keep the nitrogen blowing, quickly open the door, keep an eye on that humidity sensor. Somebody closes the door, we use the pumping mechanism. So from that gate valve is where we attach the pump and start pulling the vacuum as soon as we close the door. So we don't have to wait for it to open and then attach the pump. The gate valve allows us to attach the pump first under nitrogen purge, then open the big door, get in there, start the pump as soon as possible, and then that locks the detector in and we pull it out. We have done it like several times now. It's back-breaking work, but it's fun.
I have more questions for you.
I can walk with people if people are interested.